Okay, so good afternoon, everybody. All of you are welcome to another seminar from the Group of Orbital Dynamics and Planetology from São Paulo State University. And today we have a pleasure to have here Elodie Dufaux. She is a master degree student at the Institut de Physique du Globe de Paris. And she's going to talk about revisiting the dynamics of formation of Saturnian system, in particular the question of new satellite migration models and the implications for the case of Titans, the origin of Titans. So please, Elodie, it's with you.
Thank you. So today I'm going to be talking about the dynamics and the formation of Saturn's system of rings and moons. And in particular, I'm going to be interested in new models of migration for the satellites and how they could challenge results from previous studies that were done in this field and their implications for Titan's origin. So first, maybe I can introduce myself very quickly. So I just graduated from my master's degree, Planetology and Space Exploration at the Observatory of Paris. And I'm currently doing my internship with Gustavo and also with Sébastien Charnos at IPGP. So first, let's start with a bit of context. So there are still a lot of mysteries surrounding the Saturnian system. And one of them is the origin of the rings. We still don't know exactly how they were formed, although there have been many hypotheses on the subject, like the hypothesis of a large object, differentiated object that might have migrated inwards towards Saturn, which then would have been stripped of its tidally stripped of its material, thus forming the rings. We are also not sure how old the rings are exactly, so the results of many studies seem to imply that they're young. And the main argument for that is the measured influx of micrometeorites onto Saturn that was measured by the Cassini probe. So this pollution would mean that if the rings had been very old, they would be much darker than they are today, because we know they're composed mainly of pure ice. However, there are studies that challenge this theory, this hypothesis, and they involve cleaning mechanisms that would make the pollution of the rings a lot less efficient, thus making the rings older than they actually appear. Another problem is the origin of the satellites. So we know some satellites can be captured, but there are two main hypotheses for the formation of the satellites in this system. So the first one is, and they're not mutually exclusive, they can both happen in the same system. So the first formation scenario is the one that says that the satellite can be formed in Saturn's subnebula, but the one that we're going to be interested in today is the second one, in which a satellite can be formed from the viscous spreading of Saturn's rings beyond the Roche limit. So then aggregates can be formed, and by colliding with each other, they can form larger and larger satellites. So this was first presented in Charnos et al. 2010 and 2011, and this is the basis of my work. So there are many observations that support this scenario. And first, the age of the surfaces of the moons seem to grow with the distance to Saturn. So for example, the surface of Rhea appears to be older than the surface of Enceladus and something like that. That was done using N-body simulations and crater counting. Also, the small moons of Saturn are underdense. They're porous, so that this could mean that the satellites accrete matter. So this is realistic if we assume this scenario of the satellites forming when the rings spread beyond the Roche limit. And the spectral characteristics of the moons are also close to those of the main rings. Also, a study by Salmon et al. 2010 showed that the rings could have been initially very massive. So here you can see a plot from this article on which the y-axis represents the mass of the rings and the x-axis is the time of evolution of the simulation. So here you can see that if they input different initial masses for the rings, for different simulations, here represented by the different lines, after 5 billion years of evolution, we always end up with an asymptotic mass for the rings. So yeah, if the rings are very old, it means they could also be they could have been very massive initially. So maybe we could even form very large satellites like Titan, for example. And also we know that there are varying silicate fractions within Saturn's mid-sized moons in particular. So this is not, this can't be achieved if we assume these satellites are formed in Saturn's subnebula. Now, in 2016, Fuller et al. Proposed a new model of migration that is due to the resonance locking between planetary oscillation modes like gravity modes or inertial waves with the orbital period of a moon. So this could imply very different migration rates if we compare them to the classical models. So this prompts us to reconsider previous studies that were led in this field. So this is basically the aim of this study. What I did was I used a hydro-rings code developed by Sébastien Charnoz and then Gustavo that was presented in Charnoz et al. 2011. And then I improved it, adding these new models of migration. And so since in the classical model, Titan could not have formed from the rings because it's way too far from Saturn, and we can't make it migrate from the rings to its current position with classical models. But if we assume that the rings could have been very old and very massive, and that these new models can yield very fast migrations, then maybe Titan could have been formed from the rings and could have migrated to its current position. So I'm going to present the physical processes that are involved in the hydro-rings code and that I used. And the first one is the viscous spreading of the rings. So using a study by Daisaka et al. 2001, we can calculate the viscosity of the rings at every location in the rings. And from this, we can get the viscous torque and then the mass exchange between different regions of the disk, which yields the new surface density and the mass of the ring that spreads beyond the Roche limit. Now for satellite formation, the condition was if a satellite is close to the ring, then it can accrete this mass that spreads beyond the Roche limit. But if there's no satellite close to the ring, then a new aggregate, a new satellite is formed. Now it's well known that there are many resonant interactions between the rings and the satellites. So I'm going to be talking about the Lindblad resonances here. So simply put, this is when the orbital frequency of a satellite matches with the orbital frequency of the particles at a certain location in the rings. And when this happens, there's angular momentum exchange between the rings at this location and the satellite. So here on this Cassini image, you can see, I don't know if you can see my pointer, but here you can see a gap that was probably caused by Lindblad resonance. So at this location, the particles yield angular momentum to a satellite that we can't see here. And so the satellite can migrate outwards, while the particles here fall back, lose angular momentum, and fall back within the disk, which creates this gap here. And something that's important to note is that these interactions stop being an efficient mechanism for the migration of satellites beyond the 2-to-1 mean motion resonance with the edge of the disk. So this is a limit that's going to mark a change of migration regime, and it's going to appear in the plots I'm going to show you. For collisions, so basically we say that if the regions of influence of two satellites here represented in red can cross, then there's a collision. collision happens. And when that happens, a new satellite is formed with a new eccentricity and a new semi-major axis. That is computed using the conservation of angular momentum. And also we accounted for mean motion resonance crossings between pairs of satellites. So this gives a short-term variation of the eccentricity. We didn't account for captures in mean motion resonances. So there's no gradual increase of the eccentricity. It's just a short-term increase. So now we also include tidal interactions. So here, the phase lag model, for example, I'm going to show you. So you know that when a planet has a gravitational interaction with a satellite, there's a bulge that is formed. So if the satellite orbits the planet beyond the synchronous orbit here represented in the dashed line, then the satellite is going to lag behind the bulge. And so that means it's going to gain angular momentum from the planet, and so it's going to move away from the planet. On the contrary, if the satellite orbits inside within the synchronous orbit, it's going to lose angular momentum and fall back towards the planet. So here I've put the main equations for the migration rate and the change of eccentricity in this scenario that were calculated by Kaula in 1965. So here some important quantities are the love number over the dissipation factor here, K2P over QP. What's important to remember is if the semi-major axis A of the satellite increases, then the migration rate is going to slow down. On the contrary, if the mass of the satellite increases, then the migration rate increases as well. Now for the new models of migration, so they were first presented in Fuller's article in 2016. This model is based on the resonance locking between a moon and an internal oscillation mode of Saturn. So that could be a gravity mode or an inertial mode. So what happens is that at these particular resonances, the resonance excites the oscillation mode, which means the dissipation of the planet increases at this particular resonance. And then the satellite can gain angular momentum and migrate outwards. So Fuller took this resonance condition here between the frequency of oscillation of a planetary oscillation mode, omega A, omega alpha, and between the mean motion of a satellite NS here, and then using the two characteristic evolution timescales, T alpha for the oscillation mode and TP for the spin of Saturn, and differentiating this using Kepler's third law, he gets this formula for the migration of the satellite. So here, if T alpha increases, the migration rate is slower. And if the semi-major axis of the satellite increases, then the migration rate is going to be faster. So here is a plot from Fuller's article. So on the y-axis is the semi-major axis of the satellites, and on the x-axis is the evolution time of the system, of the simulation. So the plain lines represent the classical model of tides, the classical model of migration of the satellites, and the dashed lines represent his new model of migration with resonance locking. So we can see the migration rates are very different, and they could mean a very different orbital evolution history for the whole system. Here, what's important to note is that in this plot, Fuller assumes that all the satellites are constantly in a resonance locking situation with one planetary mode of Saturn, so it might not be very realistic. It's also the assumption that we're making in our models I'm going to talk about, but it might not be very realistic. And if we take the classical definition of QP, or the dissipation factor of Saturn, we can then find a formula for the dissipation factor when there is a resonance locking situation here. And in 2020, Valérie Lenné also computed a new model that was, this one, it was based more on inertial waves. So doing the same process, he found this formula here. And yeah, so he gets this plot. Again, y-axis represent the semi-major axis and the time for the x-axis. And what's interesting in this plot is that if we're using this resonance locking model, which is now represented by the full lines here, we can see that compared to the classical model in dashed lines here, Titan could have been initially very close to Saturn in this new model. So that's very interesting for us if we want to try to form Titan from the rings and make it migrate to its position. And yeah, also he simplified this formula here. So A is still the semi-major axis, B is a constant that you can determine using observations, and T is the age of Saturn. So as Saturn gets older, the migration rate gets smaller. So some important things to keep in mind. So as you can see on this figure here, the mass to semi-major axis relation between the mid-sized moons of Saturn here in red and the small moons here in blue is different. So that means there's a change in regime for the migration, and we want to reproduce this in our simulations. Also, it might be difficult to date Titan's surface, so it has a thick atmosphere, so crater counting might not work as well, I'm not sure. So for this study, I mostly stuck with dynamical considerations. Another way to determine the goodness of a simulation could be to compute the log number of a dissipation factor for 2 satellites over the whole simulation, of the whole hydro ring simulation. This is what I did here for 2 satellites, the 2 largest, represented by the lines here. And we can compare those with the measured values for K2P over QP that are here represented by the horizontal lines here with the uncertainties. And if the 2 lines cross their respective measured values at the same time, we would say it would be encouraging. It would be a good simulation. But here it's not. Another thing to keep in mind is that we should reproduce the current observed surface density of the rings in our simulations, and the final mass of the rings as well. And I also tried to compute the dynamical ages of the moon's surfaces. To do that for each satellite, what I did was I took the time at which a large collision last occurred, because that would mean that the whole surface would be reshaped. And so a large collision means there's a high mass ratio between the 2 satellites that enter the collision. And I set this mass ratio to be 1%, but it's very arbitrary, so I could study this more. So here you have, for one simulation, an example. So the x-axis represents the progression of the simulation, and the y-axis represents the age of the surface of these 5 satellites here. So the 0 here represents the time at which a large collision last occurred. But yeah, we would have to work more on this mass ratio of 1%, because here, for example, for my mass, we can see that it did experience a large collision, and yet the whole surface wasn't reshaped by it. So yeah, we would have to study this more. Also, we could study the tidal heat rate of several satellites throughout the simulation. That's what I did here for, again, the 5 largest satellites. And this is interesting because, for example, some satellites like Enceladus are still active today. So it would be nice to try and reproduce an accurate tidal heat rate to be able to produce this kind of activity. Now, for the results of the simulations. First, what I did was I used the classical model of tides only, without including Fuller or Linus models of resonance locking with planetary oscillation modes. So these are some results that I get. So what you can see on the x-axis is the semi-major axis in Saturn radii. On the y-axis on the left here, you can see the disk surface density of the rings that are represented by the lines here. And on the left, you can see the satellite masses, and the satellite are the dots here. The different colors represent different times of the simulation. So the red color is the last step of the simulation. The green triangles represent the current masses and semi-major axes of the satellites. And here you can see the dotted line represents the 2-to-1 mean motion resonance with the edge of the disk. So if you remember, that's where the resonance interactions with the Lindblad resonances stop being efficient as a way to make the satellites migrate. So there's a change of regime here. So this is this simulation here on the left was obtained using the same parameters, same K2P over QP, and same initial mass of the disk as in Shanos et al. 2011. But I wanted to improve this a little bit. So I added Titan at its current position. So here on this graph on the right, you can't see it. It's far on the right, but it's there. And I also added the mean motion resonance crossings, punctual crossings. So this is the simulation that I get. So it's pretty different from this one. I wouldn't say it's improved, but we get more satellites. Now, why is that? It's because the mean motion resonance crossings between satellites is going to change the eccentricities of some of the satellites throughout the simulations. As we see here, the y-axis is the eccentricity of the 5 largest satellites, and here the time of the simulation. So different eccentricities mean that the dynamical history of the system is going to be very different in this simulation compared to this one. So that's why we get more satellites. So now I also tried to change these 2 parameters, K2P over QP and the initial mass of the disk, to get a more fitting result with the green triangles. So that's what I did here. I increased the migration rate and I increased the mass of the initial mass of the disk. So we managed to get Rhea to its current mass and position. But if we compare the second largest satellite here is smaller than the second largest satellite here. So this is due to the fact that on the simulation on the right, the mass initially the mass of the rings was very high. So that means the rings spread very rapidly and they evolve very rapidly. And so the largest satellite can accrete all this mass that spreads in the first million years. And so there's not much matter left for the smaller satellites that form later on here. So that's why we get smaller masses compared to a smaller initial mass for the rings. Now, using the dynamical tides, so the Fuller model and the Linus model for resonance locking between moons and planetary oscillation modes. So if I use the Linus model here with this formula, I put it here, this is the result that we get. So obviously it's not a very satisfying result. So this is due to the fact that, if you remember, T here is the age of Saturn. So at the beginning of the simulation, the satellites are going to migrate very, very fast. So they don't even have time to interact with one another. And so this leads to smaller and smaller satellites here, basically a bunch of satellites that are very, very small. So I didn't use this model too much, but I used the Fuller model much more. So with this formula here, Now, if I take two different values for the T alpha, the evolution timescale for the planetary oscillation mode, so in this one, the migration is slower on the left, and on the right, the migration is slower. Okay. On this one, the migration is faster, and on this one, the migration is slower. Don't know if I said that right. So what we can see when we compare the two graphs is that Titan can reach its current position, but the second largest satellite cannot in this particular condition here. If the migration rate is fast, then the second largest satellite cannot reach its own position, because Titan is going to migrate faster and faster as it moves away from Saturn, and that will not leave enough time for the proto-Rhea to reach its own current position. Also, on the simulation where the migration rate is slower here on the right, the second largest satellite is larger than the second largest satellite for when the migration rate is faster. This is due to the fact that for a slower migration rate, the second largest satellite is going to stay close to the rings for a longer period. This means it can accrete more and more matter. That's why it's larger here than it is here. Now, if we keep the same T alpha for the two simulations, but we change the initial mass of the rings, so we increase the mass of the rings on the right here. What happens is, like previously, again, so we can reproduce Titan's mass and current semi-major axis, but for the second largest satellite, the mass is going to be lower compared to a lower initial mass of the disk here. This is again due to the fact that for a larger initial mass of the rings are going to spread very rapidly, and so only Titan is going to accrete this mass, and so the smaller satellites don't have much matter left. Okay, so now if you look at the purple step here, this is the very first step of the simulation, and you can see there's a satellite that has the mass of Titan, and there's also a satellite that has the mass of Rhea about. But then it's accreted by Titan. So what I wanted to do was to take a step back and again assume that Titan was formed in Saturn's subnebula and not formed from the rings. And I wanted to form the satellites up to Rhea from the rings. So that's what I did here. So on this simulation, you can see I've put Titan initially here at 4 Saturn radii, and I've tried forming the smaller satellites from the rings. So what happens is, again, a satellite that has the mass of Rhea is formed, but it's immediately accreted by Titan because it's too close to the rings. So what I did was I initially put Titan further from the rings here at 6 Saturn radii, and here you can see that the satellite that has the mass of Rhea can form, and it's not accreted by Titan. However, since Titan is further from the rings, it's going to migrate further, faster and faster away from Saturn, and so it reaches its current position very, very fast. And so Rhea doesn't have the time to reach its own position. And that's the problem I got in all my simulations, basically. Either the masses weren't correct, or the Titan migrated too fast, and so the other satellites don't reach their current positions. So yeah, so for the conclusions, we can say that forming Titan from the rings, it seems a bit complicated. We always have one of these two problems, either the mass problems or the migration problem. And so this is even a problem if Titan is assumed to be formed from Saturn's subnebula, and we form Rhea and the other satellites from the rings. So as you can see here, we don't even match the green, the current parameters of the satellite. So what we can say is that the model may be lacking important physical processes, and we're also making big assumptions, like, for example, as I've said, in the Fuller model, we assume that all moons are constantly resonantly locked with a planetary oscillation mode. But here you can see on one of Fuller's plots, you can see that the blue dips here each represent the frequency of one oscillation mode of Saturn. And so this assumption that all moons are constantly in the resonance locking situation might not be accurate, and we need to work more on this. And also, I'm working currently on accounting for the capture of satellites in mean motion resonances. So not just accounting for the crossing, but for the capture. And so that's what I'm doing currently. So what I'm trying to do is I'm using the N-body code rebound. And with this, I'm studying the interactions between two satellites. And I'm trying to see if there are captures in certain resonances, how long the resonances last, what is the increase of the eccentricity throughout this capture. And for that, what I'm doing is I'm trying to change the mass ratio between the satellites. I'm trying to change the initial positions of the satellites and also the migration rates of the satellites. So my goal would be to systematically find a way to, for all these scenarios with different initial conditions, I want to find a way to find what resonance has a capture, how long it lasts, the dE over dt, and so I may be able to implement this in hydro rings later on as a recipe. And so, yeah, that's currently what I'm trying to do. And that's it.
Okay, Elodie, thanks very much. Excellent presentation.
Thank you. Thank you.
Now we are open for questions, comments. So anybody would like to make a comment or a question? Just raise your hand or turn on your mic. Okay, Sylvia, please.
Hi, Elodie. Thanks for
Hi.
your presentation. Very nice. Thanks, Gustavo. I have a lot of questions. I don't know if I follow all the explanation that you gave. Is that possible to use this model to another planetary system?
Oh, you mean using hydro rings for Jupiter or?
Or to analyze the formation of the satellites using this, using this program?
Yes. Gustavo even used it to analyze the system of Mars, Phobos, and Deimos, if I remember correctly. So yeah, we just need to change the mass of the central object, just parameters of the simulation. But yeah, it can be done.
May I ask another question?
Of course.
Yeah, go on.
Could you go back, I think, 1 or 2 slides? No, next step. Okay, this one. What do you think it's easier to implement now among all these steps?
Yeah, the one I'm currently working on, the capture in resonances, because for the resonance locking with planetary oscillation modes, I would need to study very deeply the model of Fuller, in which he calculates all these frequencies for all the different planetary oscillation modes. And I've looked a bit at how resonance locking occurs in this article here by Burkhardt in 2014. And it seems very complicated to implement this in hydro rings. So yeah, for now, I'm focusing on the capture in mean motion resonance. There are other steps that I didn't talk about all of them because to me they're not as urgent as the capture in mean motion resonance, because this could really change the whole history of the system. with continuous increases in the eccentricities. I think it's really the most important one for now.
Okay, thank you.
Thank you, Sylvia. Anybody else? Any other question, comments? Hi, William Botek, please open your mic.
We have a number of people that watched the talk and we enjoyed it. Alyssa Roden has a question.
Hi. I wanted to ask about the heating of the moons and geologic activity.
Sorry, I can't hear you very well.
Okay. Give us a second.
Yeah.
Okay. How about now?
Yeah, it's fine.
Okay, great. So I wanted to talk about this heating of the moons and geologic activity bullet point that you have here, because one of the ways that this could affect your models is through the K2 over Q that you're assuming for the moons. So especially if you go into adding mean motion resonances and increasing the eccentricities, you're likely going to have a case where you go from a solid moon to something that's melting, or something that could have liquid water that will be more tidally responsive. So as you're doing the mean motion resonance problem, you may want to consider testing what happens if you change the K2 over Q of the moons as you're doing the tidal evolution. So just a thought.
Yeah, that's something I hadn't really considered at all. Okay, that's very interesting. Thank you.
Good, thank you. Any more questions? No, I had a point. It was more or less related to what has been said. It's since you keep this tidal parameters constant, might be as the body grows. So you may have some changing in these parameters that might be the difference.
So you mean, sorry. Oh, yeah. You mean the K2P over QP?
Yes.
Yes. So basically in the in the classical model of tides, it's kept constant, and it, to my knowledge, it always has been in previous studies, except maybe one. But for the new models of migration, actually, what we're using is this Q factor here. That accounts for the mass of the moon, it's my major axis, etc. And we're taking measured values for K2P. And so this K2P over QP is not constant in our new simulations.
Okay.
That was the question.
Yes, that was the question. Okay. Thank you. Okay, any more questions or remarks? Go on, please.
We have another question, if that's okay.
Yes, that's fine. Yeah, feel free.
Go ahead, Miriam.
Okay, hi, Elodie. Very nice talk. Just wondering, based on your assumption with the Fuller model, this migration type required that all the satellites need to be in mean motion resonance all the time. We know that it's not true, unfortunately, but you said at the end that you are gonna work on the time scale of the resonance. I'm just curious, how are you going to change that model? And slightly just a second question, in your slide 35, you put the match ratio about 1%. I'm curious how did you
Mass ratio,
that?
oh yeah. For this question is very quick to answer. It's just really arbitrary. It's because 1% is pretty high. It could potentially create a big collision, but it's very arbitrary. Yeah, we definitely have to work on this. And I already forgot your first question, sorry.
The Fuller model about the fact that the moon are always in mean motion resonance. How are you going
so we're not assuming they're in mean motion resonance.
in resonance locking, sorry.
Sorry?
In resonance locking?
Yeah, with planetary oscillation modes.
Yes.
Yeah. Oh yeah, and so right now I'm not sure exactly how I'm going to address this issue because I've read articles about when we can have a resonance locking with planetary oscillation modes, and it seems very difficult to implement, especially in a 1D code, one-dimensional radial code such as hydro rings. So yeah, I'm a bit procrastinating on that and focusing more on mean motion resonances. But yeah.
Like,
Okay, good. Sylvia again.
Oh, hi. Next step, could you put the next step slides, please? When you include the last one, secular effects, do you mean between the satellites?
Yes. Yeah. So actually, Gustavo implemented a method to calculate the secular effects between all the satellites, but I didn't use it at all in hydro rings because it makes the simulations very, very long. But it is present in the code. So yeah, we'll see about that.
Okay, thank you.
Okay, go on, Botka.
Okay. I just wanted to ask a sort of a big picture question, which is that let's say your model would have succeeded and you would create the satellites and Titan as well.
Yeah.
What does that mean for Iapetus? Does that mean, do you have to have a very specialized gas disk for Iapetus?
Not really. Yeah, no. I have no idea. No, sorry.
Okay. Thanks.
Thank you.
Okay, good. Any more questions or comments? No? So let's thank again, Elodie. Thanks very much for your presentation.
Thank you.
It was really
Thank you for
interesting.
having me.
Okay. So thank you very much.